Okay, real quick. So now what do we call this? I've got these two lines. They're cut by this other line. What do I call that line?
Transversal.
Transversal. Yeah. And transverse means across, by the way. So that's a good word for that. So that's our transversal. What do we call, let's see, what about angles, if I want to take the pair of angles 3 and 8? What do I call that relationship between angles 3 and 8? Alternate interior. Very good. They're alternate interior.
Good job.
So, now that's exactly right. How'd you get that? What about them is alternate? Do you remember?
They're on different sides.
Yeah, they're on different sides of the transversal, right? Alternate means opposite sides of the transversal. And then interior because they're inside the two lines, right? So that's how we name them that. What about angles? Let me give you a tough one here. What about angles 1 and 7? That's kind of a tricky one. It's a little bit tricky. Think you got it, Sean?
Corresponding exterior.
Okay, almost. Starts with a C. No, it's almost right. They're exterior, and it starts with a C, but it's not corresponding. It's you remember? Okay, now so alternate means they're on opposite sides of the transversal. What do we say if they're on the same side?
Congruent.
What was it again?
Consecutive.
Consecutive. Yeah. So. Consecutive exterior. Okay, what about, let's go angles 2 and 5. 2 and 5. What do you think? 2 and 5. Brady? 2 and 5. What do we, remember what we call that relationship? 2 and 5? No? Martin, remember that one? 2 and 5.
No, I don't remember.
Riley, remember that? Say it again. 2, no, not collinear. Corresponding. Yeah. Okay, now why are they corresponding, right? What does it mean to correspond? To correspond means that they are the same, right? There's two ways you can think about that. It's been a while since we did this, but remember one way that I think is good is if I take one of those two lines and I drag it down on top of the other line, wouldn't you agree that angle 2 would just become angle 5?
Yeah.
Right? Okay. The other way of thinking about it is they have to have the same relationship to their line and the transversal, right? Angle 2 we would say would be what? The upper right line, upper right angle. Angle 5 is the upper right angle also. Okay? So they're corresponding. Oops. What about, let's do one more. What about, how about angles 4 and 5? Okay, does that make sense? Alternate interior, opposite sides of the transversal, but inside the two lines. I lied, let's do one more. How about 3 and 5? 3 and 5. What do you think? Abby, you think what 3 and 5 would be?
They're interior.
They're interior, good. Oh, Sean's got this one now, what?
Consecutive.
Consecutive, good. So together that's it, right? Interior. Consecutive because they're on the same side, interior because they're inside.
I'm giving up.
Okay, make sense? Okay. All right, so here's what I want to do then. Oops, that's not what I want. That's what I want. Okay. Okay, so here's what we're looking at today. Real simple. This is probably, I don't know how much review this is. It might be a little bit review. It may not be at all. I can't, it kind of, I don't know. All right, so what we're going to look at today is the case where the two lines that are being cut by the transversal are parallel. If those lines are parallel, then that tells us a lot of stuff about that whole bunch of angles, about the relationships. Okay, for one thing, we know the corresponding angles postulate tells us, and this makes sense. This is something, it's a postulate, so it's something that we're just taking to be true because it's very obvious. The corresponding angles postulate tells us that if two parallel, and that's the symbol for parallel, right? If we just have two vertical lines, and sometimes you'll see them when they're slanted a little bit, but if you have two, short pieces of line, little segments that appear to be parallel, that's the symbol in geometry for parallel. So if two parallel lines are cut by a transversal, then all the pairs of corresponding angles are congruent. That's always true. Now, we can convince ourselves of that pretty easily, I bet. Now, what does it mean? First of all, how do I know that lines L and M, based on the picture, how do I know that they're parallel? Okay, because, those are supposed to be arrows because they each have a single arrow, right? So that means that they're parallel. All right, so this postulate tells us that they're congruent. Well, doesn't that make sense, though? If lines L and M are parallel, wouldn't you agree that if I were to drag line L straight down onto line M, angle 1 and angle 2 would have to exactly line up? Everybody agree with that? Okay, so we can see then, for that reason, that if they're identical angles, they must be congruent, right? And so we come up with this postulate. All right, so in this case, angle 1 and angle 2 are congruent. Now, from this, we can get a bunch of other stuff. If we start with this corresponding angles postulate, we can get a bunch of other things. For example, we can get the alternate interior angles theorem. Okay, we now know that if two parallel lines are cut by a transversal, same hypothesis as before, right? All of these new theorems that we're about to learn, they start the same way. If two parallel lines are cut by a transversal, then, well, in this case, this theorem tells us that all the pairs of alternate interior angles are congruent. Okay? So if the lines are drawn this way, then angles 1 and 2 would be congruent. Okay, now I don't have you do a lot of proof in this class. The research just all seems to indicate that that's really not a very important thing to do in a geometry class. But I do want to show you occasionally, go through a proof with you. So you can kind of get an idea of what a proof looks like, how is it structured. Proof is a big deal in math. Later on, if you take more math classes, in college, it's likely that you might actually end up having at some point to maybe do a little bit of proof. So all this is, a proof is just a list of statements that are going to take us from some initial given information to some statement that we're trying to show is always true. Okay, so in this case, we want to prove this theorem. So what do we know about this? Well, we're told in this theorem that if two parallel lines are cut by a transversal, so we're told that these lines, which we're going to label L and M this time, are parallel. That's just given to us. We don't have to show that. That's something that we're assuming to be true. We want to get down to the point now where we can show that angles 1 and 2 are congruent because those are alternate interior angles, right? Okay. So what can we say here? Well, we could start off and we could add this angle 3. And why is it that angles 2 and 3 are necessarily, why do they have to be congruent? What's our reason for that? Can you think? Okay, because they're corresponding. And the corresponding angles postulate that we just talked about a few minutes ago told us that if parallel lines, these are parallel, are cut by a transversal, then corresponding angles have to be congruent, right? So the reason for that is what we might call the corresponding angles postulate. That's our excuse for making that statement. Okay, so if we know then, I want you to see if you can kind of work your way through this. So if we know that angles 2 and 3 are congruent, I'm trying to show that angles 1 and 2 are congruent. Does anybody think of a strategy here? What do you think? Christian, you have an
3
idea?
and 1 are vertical angles.
Okay, so we could say that 3 and 1 are vertical angles, and so they're congruent, aren't they? Right? Does that make sense? Now, if 3 and 1 are congruent, and 3 and 2 are congruent, doesn't it make sense that 1 and 2 have to be congruent then also? Right? And there's some reasons for that I'm not going to spend too terribly much time on. But that's our next statement. 1 and 3 are congruent, and the reason is because they're vertical angles, right? The vertical angles there. So now all we have to do is say, okay, well, if 3 is congruent to 2, and 1 is congruent to 3 also, then 1 and 2 are congruent. Okay, and the reason for that is what we call the transitive property of congruence. But all that really means is if something is, if 1 is congruent to 3, hang on a second. If 2 is congruent to 3 and 3 is congruent to 1, then we can skip the middleman. We can skip the angle 3, and we can just relate these two directly, right? That's what it means to be, that's an example of a transitive property in math. And we got it, right? There's our proof. Now that we've proved this is something that we could always use. And it's called a theorem. So once it's been proved, we can add it to our toolkit, right? That's something we can always use in the future. It's a relationship that's now solid for us. Okay, we get another one. We also get the consecutive interior angles theorem. It's a little bit different though. The consecutive interior angles theorem doesn't say that the consecutive interior angles are congruent, but that they're supplementary. So once again, if 2 parallel lines are cut by a transversal, then all the pairs of consecutive interiors add up to 180. Their measures do. They're supplementary. Okay. So let's look at just a really quick little, oh, hang on, I guess we're not going to prove that one. What about alternate exterior angles theorem? Okay, alternate exterior angles. If 2 parallel lines are cut by a transversal, then the pairs of alternate exterior angles are congruent. Okay. So in this case, that would be angles 1 and 2. Okay, we could prove that. Honestly, the proof would look really similar to the one we just did. We did alternate interiors, but alternate exteriors we could do in the very same way. Okay, another one. They skipped a couple, and I'll come back to that. The perpendicular transversal theorem. Okay, this one just makes sense too, really. If a transversal is perpendicular to one of 2 parallel lines, then doesn't it also have to be perpendicular to the other one? I mean, it just kind of makes sense. Right, so if I've got these 2 lines, L and M, that are parallel, and they're cut by some transversal, so that lines L and the transversal, which maybe we'll call T, are perpendicular, then doesn't T also have to be perpendicular to M? Okay. Yes, it does. So we have that one now we can use. Okay, let's take a quick look at a proof for that. So we got our statements and the reasons that allow us to make those statements. Well, just like before, we can say that we know lines L and M are parallel, and we also know that the transversal is perpendicular to one of those 2 lines, right? So we'll say line L. That's given to us. Now what can we do? Well, we could say we need a picture. Where's our picture? It's kind of inconvenient. Hoping we get a picture. Oh, never mind. I tell you what, that one doesn't make much sense without a picture. I'll come back and do that one later. Don't worry about it. That's you got to be able to look at a picture though, or it doesn't make a lot of sense. Okay, these are the kinds of problems I like the best. The problems where you're given some kind of geometry relationship, and in chapter 3, the geometry relationships that we're going to focus on are going to mostly be about transversals and pairs of lines, right? So what can you tell me just about this right now from this picture? What do we know about the lines? They're parallel. Yeah, so that tells us a bunch. If I know those lines are parallel, then I should be able to figure out fill in all the other blanks, right? I should be able to find the measure of angle 1, measure of angle 2, and so on. So let's try this. Okay, what about the measure of angle 1? How am I going to find that? What do you think?
125 plus x equals 180.
Okay, 125 plus that angle has to equal 180, right? They're supplementary. How come? You're right. How come?
Because they're on the same line.
They're on the same line. What do we call that relationship? That's a linear pair. Yeah, good. If I get two adjacent angles that make a line, right, then they're a linear pair. So all I'd have to do is just subtract 125 from 180, right? So what is that? 55? Come on now. 55? Okay, oops. What about angle 2? I gave that one away. That's an easy one though, right? Why is it 125? That's an easy one. How come it's so easy? What's that relationship?
Vertical angles.
Vertical angles. Yeah, if they're opposite angles, when two lines cross, all the opposite angles we call vertical angles, and they're always congruent. So then what's the measure of angle 3?
55.
55. Yeah, it's got to be the same as 1, doesn't it? Right? Okay, what about angle 4? Whoops. What's angle 4? How come? What is it?
They're equal to each other.
But how? But why? What's the reason? Why 4 is 125?
So many words corresponding.
Ah, corresponding, right? Okay, that's what I'm looking for. Okay, that's what I'm looking for. They're corresponding angles, and so they have to be congruent. Okay, now once I know that the measure of angle 4 is 125, the other ones are pretty easy, right? So what's the measure of, Bailey, what's the measure of angle 5 going to be? Well, keep in mind, here's a bunch of stuff that might be helpful. We already know a bunch of these other angles, right? So let me ask you this. 5 would have to be the same as which angle up here? 1. Yeah, good, right? Because they're corresponding, aren't they? So it'd be 55. Good. But what about 6? What was that one going to be? Everybody? 125, because 6 would be the same as 4, right? Now, if I want to solve for x, that's the next one. If I want to solve for x, how's that going to work?
55.
Okay, so if the measure of angle 5 is 55, then I must know that this has the same measure, right? So I've got the equation then, x plus 15 equals 55, so I just solve for x, just subtract 15, right? Okay. And I get x equals 40. No big deal. All right. Okay, so I want to help you out with something here. This is kind of a handy tool. This is called the principle of exaggeration, and it's extremely helpful in math and even in science sometimes. All the principle of exaggeration says is that if I've got, let's say I want to remind myself of all those relationships that we just talked about, right? I might want to have a picture that goes with that to remind me. Because it's easier to think about things, I've said this a million times, it's easier to think about things in terms of an idea or a concept than it is in terms of memorizing something, right? So if we want to remember the relationships, if I've got parallel lines cut by a transversal, I want to remember all of those relationships that we just talked about. I want to get a picture going. So here's my picture. I've got two parallel lines, and I'm going to cut those lines with a transversal. Okay, I'm gonna say that the top picture is a lot better than the bottom one for reminding myself about all those angles. Okay, I want you to think about why that might be true. Let's label the angles real quick. We'll call that 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Somebody tell me a relationship here between angles 2 and 8. Are they, what do you know about those angles, 2 and 8? Okay, they're alternate exterior. And are they, what about them? Are they congruent? Are they supplementary? Are they, what do you know? They're congruent, aren't they? Okay. That's easy to see up here though, isn't it? If I draw, I've got these two parallel lines. If I draw the transversal at an obvious angle, so then every time it cuts across one of the lines, it's going to create pairs of acute angles and obtuse angles. It's pretty easy to see that the acute angles all go with the acute angles, right? Does that make sense? And the obtuse angles go with the obtuse angles, and an acute plus an obtuse probably does what? Equals 180, right? The measures equal 180. And so if you exaggerate the transversal so that it makes an angle that's really obvious, it's easy to see those relationships. Not so much down there though, right? If I wanted you to tell me what the relationship is between, say, 1 and 8, what would we call those angles, you suppose? Angles 1 and 8? What do you think? Maria, any idea? It's a tricky one. 1 and 8? Consecutive because they're on the same side of the transversal exterior, sure. Do you think consecutive exteriors are going to be supplementary or congruent? Congruent? Down here they kind of look congruent, don't they? But if I look on this one up here, they're pretty obviously not congruent, are they? Right, 1 and 8. 1 is obtuse and 8 is acute, right? So they're supplementary, right? But it's confusing. That's why we don't want to draw the picture like this, because it's not obvious, right? I mean, hopefully we'll just remember the theorem, but probably not now. We just saw them, right? So you get what I'm saying about this, though? When you draw the picture to help yourself organize your thinking, make sure you make that transversal, pretty slanted, right? So you can see, you can definitely distinguish acute from obtuse angles. Okay, last issue I want to take a quick look at is another one of these. Okay, I gave you one yesterday that we went through as an example, and I got thinking about that, and I don't think it was, I think it was almost too easy in a way. It's one that worked out really well, and you may not always get that kind on the test. So let's look at one that's maybe not so obvious. Let's try to solve this system. Right now, if you look at all these, and what I think might be a good idea is to draw a picture, right? And let's go here's the picture, and let's just write in the expressions for x's and y's, inside the angles that they correspond to, right? So angle FHZ is the upper right one. That's got a measure of 5x plus 4y minus 76. Angle ZHI is the upper left. Got a measure of 4x plus 5y minus 68 degrees. And then IHM is the bottom left. 2x plus 3y minus 8. Okay? Unfortunately, there's no way, if I want to find, and the question here is just asking us to find the measures of all those angles. There's no way I can just pick x's or just pick y's, is there? Each of the angles has both x's and y's. So I'm kind of stuck, right? I'm going to have to come up with equations that involve both x and y. So what's one geometry relationship that we can utilize here? What do you think? Carolyn, you have an idea? Can you see an angle relationship here? And I don't care, if you want to just call the angles like upper right, upper left, that's fine. Can you see a relationship up here that we could use? Like, for example, the upper right angle is what? Fill in the blank. How about congruent to? Is there an angle that this angle up here is congruent to? I think. Bottom left, sure, right? Does that make sense? Because they're vertical angles. So there's an equation, right? I know this is true, so we can turn that into an equation. So this expression then, because that's the measure of the upper right angle, so 5x plus 4y minus, oh, what's that? That's, I don't know what that was. Minus 76 equals 2x plus 3y minus 8, right? So there's an equation now, but keep in mind, don't lose sight of what we're trying to do with this. The x's and the y's are going to both stick around, so we're going to need two equations, aren't we? Right? So if we need two equations when we're solving a system like this with x's and y's, remember what we wanted to do. We wanted to get the x and y terms on the left and the numbers on the right. That was the best way to do it. So how would I accomplish that algebraically? What are the steps I want to use then? Okay, so how many x's am I going to add or subtract to both sides? Subtract 2x, right? Okay, that's a good idea because that's moving the x's to the left side. So I'm going to get 3x. What about the y's? Subtract 3, good. Subtract 3y. That's going to give me 4y minus 3y is y. They cancel over there. And then what about the numbers? What do I want to do with the numbers?
Adding.
Good. I could add 8, but I want to get the numbers on the other side, right? So what might I do instead? Add 76. So those cancel. And positive 76 plus negative 8 is what, 68? Okay, so there's an equation I can use, right? Okay, what's another relationship that we could use here? Okay, what do you think? Can you think of another one that I could use? I know that these two have the same measures. What else? And then, so those two are what? What kind of relationship do they have? You're on the right track. Yeah, good, they're supplementary. So they add to 180, don't they? Right, so then this pair, I'll just circle them in blue. So that pair, their measures have to add up to 180. So there's my other equation. Let's look at that one. So 4x plus 5y minus 68 plus 5x plus 4y minus 76 equals 180. Same drill. We just want to get the x's and the y's on one side, the numbers on the other side. So this time, here's my equal sign. All the x's and y's are already on the left. I'll just combine like terms. 4x plus 5x is how many x's? 9x. So those are accounted for. 5y plus 4y. Good, 9y. So we took care of those. Negative 68 and negative 76 is negative 144. Is that right? Equals 180. What's my last step? Add 144. Come on. So I get 9x plus 9y equals 324. So I've got two equations now. Let's call this one equation 1 and that one equation 2, right? And all I have to do now is just solve that system. So there they are. There's my two equations. What am I going to do to solve this system? Got a couple options. Right, this goes back to that algebra review. What do you think? Savannah, you have any ideas? No ideas. Okay, what do you think? Somebody else, help me out. Justin.
You could use substitution.
Okay, I could. Which variable would I substitute for? Okay, yeah, it's easy for me to isolate the y in the top equation, right? So that'd be good. I could solve for y in the top equation and then substitute into the bottom. That's probably the easiest thing. What else could I do here? What do you think, Sean?
What's the one where like, you like cancel them out?
Yeah, okay, so we could use elimination or linear combination, whatever you want to call it. So what if I want to use that one? What's going to be, let me make this a little smaller. Okay, so what could I maybe multiply the top one by so I could eliminate a variable instead? What about -3? That'd be good. If I multiply by -3, then I'm going to end up being able to cancel the x's, great?
Or -1 and cancel the y. Is that easy?
Or -9?
-1.
How -1?
Or-
Because I've got 1y and 9y, right? I'd have to get opposite numbers of y's. Does that make sense? I'd rather multiply by the smallest possible number, so we could multiply by like -3. So I would just do this. What am I going to get in the top if I multiply all the way through by -3? -9x minus 3y equals some big number. So that's going to be -204. And then on the bottom, I'll just leave it the same, right? Bottom can stay the same. I just get 9x plus 9y equals 324. Add them up. The x terms cancel, right? That was our goal. -3y plus 9y is what? 6y. Yeah, good. Positive 6y. And -204 plus 324 would be what, 120? So how do I solve for y? Yeah, divide by 6. And I get y equals 20. We're halfway there. I'll substitute into probably the easier of the two equations. Which one's that look like? Top one. So I could just substitute right there. And if I do that, I get 3x plus 20 equals 68. So what are going to be my two steps in order that I'm going to go through to solve for 68? Kristen, what do you think? If I want to get the x by itself, what do I do? Subtract 20 and then divide by 3. Exactly. So if we subtract 20, we get 3x equals 48. Divide by 3, and I get x equals 16, right? So I've got x equals 16, y equals 20. Now all I have to do is just go back and, yeah, plug it in, exactly. Right, so if I plug those in, I'd get my answers. When are we out of here?
2 minutes.
2 minutes? So I may not have time to do that, but everybody could do that, right?
Yeah.
It's not a big deal, okay?
I haven't done it yet.
Two minutes.